invitation to, well, actually to be a part of the conference with such a remarkable university. I mean, really remarkable because it consists of first 3 simple digits. None of us probably will survive till the next so beautiful anniversary, of course, and I wish you, the department and the university, to continue, just succeed to this age as well. Okay, so there's something, just a reference when the paper will appear here, and it will be in Journal on Convex Analysis. Okay, so there were a number of publications recently concerning second-order conditions. I will give some lists at the end of the talk. And in a sense, it's a bit surprising that something new could be said about such a traditional topic as second-order condition for a minimum. Okay, that's it, right? I'm sorry. Okay. So this is the problem I'm going to discuss. And this is a problem of minimizing functional like this, which is a composition of a continuous sublinear function and a smooth mapping over x belonging to some set which can be arbitrary. And this is a really reasonably new element that attracted some attention recently when we minimize a reasonably good function on a set that can be very bad. And so I'm sorry. Just have to organize my notes. I'm sorry. Well, and this is actually the main point that attracts attention. How to write conditions of a minimum when the set on which we are working is really not very good. That's it. So, okay. So, as I told already, I'll be interested in both necessary and sufficient conditions for a problem, for a local minimum in this problem. Well, the problem does not contain functional constraints, this is written here, but actually many, well, practically all reasonable problems that appear in optimization can be reduced to this form. Yeah, that's I mentioned, just a reference to one of the papers with some good conditions were written, second-order conditions for just a simpler version of this problem, minimization of a smooth function on an arbitrary set. Okay. Well, for instance, if we have a problem of minimizing functions subject to this kind of constraints, and this is a fairly general, actually, statement, then under very general regularity conditions, which I will not formulate, but it's basically said that this mapping is, well, in a sense, is onto with this fx minus d is the covering mapping. But anyway, so under very general regularity condition, this problem can be reduced to minimization of this type of function, with k sufficiently large, subject to this constraint, which is already of the problem of the form which I stated. It's already a composition of a convex function, actually a simple convex function here, and smooth mappings if both f and f capital are smooth. Okay. So let's go further. Okay, I wish to start with some technical preliminaries. I want to introduce some concepts which probably many of us, not probably, but almost certainly most of you know, are acquainted with. So the first is the concept of subdifferential. If we have a convex function, phi, on a Banach space X, then the subdifferential of the function at a certain point is the collection of linear functionals for which this inequality holds for all h in X. Unfortunately, I cannot draw a picture, but anyway, so it's a very simple inequality for convex functions. And the main properties I need is that if phi is a continuous function, convex continuous function, then this set is non-empty, weak compact convex set necessarily. But in general, when phi is not necessarily continuous function and even convex function, we can write this function, which is a lower directional derivative of phi at x along h. That's it. By definition, it is lower semi-continuous as a function of h. Okay? Then, if this set is non-empty, okay, let it be convex. I just forgot to explain what is df of x when the function is not convex, which is possible to write as well. So then we have this type of equality always. Well, actually, let me tell you in detail, just a table if I didn't notice this before, that, oh, I'm sorry. We can write, as I told you, we can write this lim-inf for any non-convex function, and actually this type of inequality, but with this difference replaced by this derivative, will be the definition of the subdifferential for non-convex function. Okay. The second is the concept of a tangent set. So we have, if we have a certain set U at certain point x belonging to the closure of U, so really even don't assume this set U capital closed, then the tangent cone to this set at x is the collection of vectors h such that this equality, the distance from x plus t mh to u is O small of t m for some positive sequence of positive time m going to 0. That is it. There's a standard definition, everybody knows. The definition of a second order tangent set is a bit less common, but anyway it is equally simple. So the second order tangent set to u at x along h consists of all vectors v such that this equality, well, very similar to that, but of the second order holds. For some, again, Tm converting to 0. So a good thing to understand the structure of this set is that if v belongs to the second order tangent set at h, then this sum belongs also to the set for all lambda. This means that this could be a pretty big set, actually, if it is non-empty. Okay. The third concept is the concept of the normal cone. It is really a very simple thing. It is a polar of the tangent cone. Again, I'm pity that I cannot draw it as a very simple thing. Okay. It's called Duni-Damar normal cone. There are some other concepts of normal cone and non-smooth analysis, but we don't need them. Okay. The first is the concept of subtransversality. Well, actually, you will have a special lecture about transversality and subtransversality later today. So I just introduce the definition because I will use it. The definition is simple. It's basically a relatively new concept for arbitrary sets. So the definition is very simple. If you have a two sets and the point x bar belonging to the intersection of these two sets, then the sets are called subtransversal at this point if there is an n such that this inequality holds. Needless to explain, it's a very simple inequality for all x close to x bar. The concept of transversality is a bit more complicated, although all the concepts, it's really more or less the same, but when the inequality equal to not just to S1 and S2, but some shifts of the sets, some small shifts of the sets from this point. But anyway, we need only subtransversality. I need only subtransversality in the talk. Okay. The fifth point I would like to bring your attention to is the point of unconstrained reduction of optimization problem. So if you need to minimize certain function f on a certain set Q, where X is a metric space, not necessarily even Banach space, and F is Lipschitz in neighborhood of this point, then this result holds. If X is a local solution to the problem, local minimum, of course, then it's a point of unconditional local minimum of this function, where chi is greater than the Lipschitz constant of F. That's it. So we can reduce problem with constraints, provided less the cost function is Lipschitz. You can always move constraints, certain constraints, to the functional. You come to unconstrained minimization, okay? That's it. Okay, now let me come back to the basic problem. You remember this basic problem? It is the problem of minimization of function like this, okay, on a certain set U. So the first order necessary condition is this one. This is the directional derivative of this g functional at point y bar, when y bar is f of x bar. Okay? My goodness. Along this direction is non-negative for all h belonging to the tangent cone. It's a fairly trivial result. You just need to take this directional derivative and take it. And also it's good to know that if this set, the image of this set under this derivative is a convex, then the set of Lagrange multipliers of the problem. Well, it's reasonable to call this this y star. I'm sorry for that. It's not needed here. It's called the Lagrange multipliers. So this set is non-empty. If this set is convex. But I don't think I need it really for the results of this last command. Okay, but anyway, it's good to understand. So this is first order condition, very simple, necessary condition. Oh, by the way, I forgot to tell in the beginning that in the title it's written sufficient conditions in the program, but I then erased the word sufficient in the title because, well, when I sent the abstract, I didn't know that I would have 50 minutes, so I thought this would be a short talk. So. But necessary conditions are actually meaningful here, yeah. Okay. So this first order conditions, necessary condition. And this is the second order necessary condition. Consider this set, which is called critical cone. It is really a cone because it is a sublinear homogeneous function as a function of h. So this is a critical cone. The necessary condition of this quantity is always non-negative in this set. So I would be able to write here equality, of course, but it's better to just to keep it like that as far as we will come back to sufficient, we'll come to sufficient conditions. But anyway, so you have to keep in mind that, of course, if this holds, then this will have actual equality. So this is the second order condition. This is the second order condition which says that the maximum over subdifferential of function g of y bar, maximum over this, yes, of this quantity is non-negative. Again, it's not as trivial as this fact, but also sufficiently simple. You have to just to take second derivative and look a little bit what happens there and just make some calculation, not very complicated. So in particular, this holds, of course, for such h and d. Well, this is not needed actually, but of course. So this is the second order conditions for this problem, necessary condition. Well, this is also already has some new elements, and I would like to demonstrate them on the standard problem of Hagel's variations. Actually, I will just speak about the result I was telling about last year here. It was exactly a necessary condition for this problem. And you will see that this has some very interesting new elements that never appeared in classical theory before. So let's consider this problem as the classical problem of Hagel's variations under good assumptions, whatever good you need. So to write this problem in the form of the basic problem, we should set g equal to this function, just integral of y, and f is this mapping, okay, and u is this set. Very trivial. So applying proposition 2, which can contain second order necessary condition for general problem, we can get a necessary condition for a weak minimum if we consider, with respect to the C1 topology, in the form of the Euler equation only. But what about the strong minimum? Minimum with respect to the topology of uniform convergence of x alone without the derivatives. Okay, so let me state some classical result, which is the Weierstrass condition. So this is a Weierstrass function. Well, in the first 10 pages of every book on Hagel's variations, you will see this function. Wait, I'm sorry. And the Weierstrass necessary condition for the strong minimum is this one, that along the trajectory, this quantity is negative for all w and all t. And this is the first order condition. The second order condition for a strong minimum Well, as it was stated on the recently, and here it is. Well, actually, again, in the classical calculus variations, second order conditions for the strong minimum never considered. Well, it is very interesting. Well, I think that the reason was that the strong minimum was not felt as a really local minimum. So, because derivative could be arbitrarily big and so on. But anyway, so it was a big strange, but it was so. So, and this is the condition which I would like to formulate. As I told you, I actually spoke in details about this result last year. So, that WT will be the set of zeros of this Weierstrass function as a function of W only. AT, CT, and BT are all standard derivatives along the trajectory which appear in classical second order conditions in any book of calculus variations. And this is a theorem. So if xt is a strong local minimizer in the problem, then this inequality holds for any WT with values from W capital T and any B of T non-negative. I wrote here 2 because it's just more convenient for calculations and so on. Subject to this, where H and B are connected with this kind of equation. Well, if W of T consists of just of x bar dot only, or if B of T is equal to 0, then what we get here without this is the standard second order conditions of calculus variations, from which we get the Jacobi equation and whatever. So all the classical stuff. But this result is really different, and I had a simple example which I again discussed in details last year, and this will appear in the paper to which I referred to. The simple example, very simple example indeed. Well, I just, again, okay, really very simple example. And this is an example where all known necessary conditions are satisfied, but this one not. So it is, at the same time, so this means that this is a working condition. At the same time, this condition is, well, not very strong, because it works only with this set W of T. And if this set W of T consists of 1 point, we have nothing. So it's a necessary condition, but it is, well, okay, hardly be a basis for a sufficient condition. That is the open question that remains, so I will say. Okay, that is that. Yeah. I want to return to the theorem. The theorem remains a calculus variation, so I speak still about this problem. The key role in the proof of the theorem is played by this result, the Bulgaria theorem of 90-30. And this really remarkable theorem, which says that if we take the convexification of this function with respect to u, then if x bar is a strong local minimum in the problem, then it is also a strong local minimum in this problem. This result remained unnoticed for just quite a long time. And actually, for those who worked in optional control, they probably must know works of Jack Varga of the beginning of 60s, where he reinvented this, still without knowing this Bulgaria's result, actually. Yeah, so. And as I told, this result played a key role in the proof of the theorem. And the way it is proved is the following. So let's consider this function, where w of t is a certain function with values in w capital. You remember what the w, the set of zeros of the very short function. And b of t belong between 0 and 1, measured. Then by Bogoliubov's theorem, the minimum of this result, of this function, will be the same as in the original function, okay? So now, okay, using reduction theorem, along with some estimates for the distance to the set of solutions to the equation, and so on, we can show that x bar is also a local minimum to this problem under this type of constraints. And this already is the basic problem. So we can apply the necessary condition for the basic problem and we get eventually this result. So this is more or less how it works. Okay. Now let's go back to the basic problem. I wish to recall the notation. This is a critical cone. We assume, of course, that x bar is a local minimum in the original of the basic problem. And TUX is a tangent cone to U at x bar. And for H belonging to this tangent cone, this is a second order tangent set to U at x along H. Okay? And the second order necessary condition which I wrote there is this one. Well, it's the wicked form of the necessary condition, but that's enough. If H belongs to KC and K belongs to its second order set. So this is what we have already. So we want to go further a little bit and pass sufficient conditions to this basic problem. Well, the main assumption to get the sufficient second order sufficient condition of this problem is that the tangent set, this and this, the critical cone and the second order tangent set, will approximate the needed part of the, well, of the feasible set. Namely that this condition A is satisfied, which is a bit complicated. So this condition says that for any lambda, we can find this epsilon such that for any u belongs to, well, this set, u minus x bar, smaller than epsilon, and such that this is closer. You remember that necessary condition is this is smaller than epsilon, and than 0. So we need to consider only small positive values here. We can find vector h and v such that this type of inequality, this inequalities hold. That u is well approximate h, and h is well approximate u, I'm sorry, and h plus v is well approximate u plus lambda u squared. U squared. Okay. This is not a simple condition, unfortunately. And verification of this condition, well, in problems may require some effort. So, but anyway, so this is the theory. So, assume that this condition holds, then this inequality, when instead of 0 we write h squared times some positive quantity, satisfied for all h in critical cone and all v in the second order tangent set, then x bar is the local minimum, subject to x belonging of the function j subject to x belonging to u. So this is the key condition. And the big part of the proof of this, well, the proof requires some effort, it's not a trivial thing even under this condition, but actually the main thing just to allow us to be able to just use this condition is to understand how we can get this condition, how we can verify this condition at least. So let me start with that. This proposition offers some sufficient condition for A to hold. The first condition is very similar to A actually, but it applies only to the set U with no mention of the function. This is the first condition. If you look at U, you will see this is basically the same, but this is absent there. And the second condition is this one. Oh, I'm sorry. And the second condition is this one. That this inequality holds with some n, the distance from U to Ks. Already for any U, no, it should not be an element of U bar and so on. Of U bar minus X bar, of U minus X bar, I'm sorry. Okay, so if these two conditions are satisfied, then A holds. So we now have to understand how to check these two conditions, of course. I just want to mention two cases when these conditions hold. When the first condition holds, condition I. It holds when this inclusion is valid, in particular when U is a union of family of convex sets. So it means that the tangent cone contains the set. Well, the difference between the set and the point, at least. The second point is that when U is this set of finitely many inequalities and possibly infinite dimensional equality, okay? Under the assumption that the functions Gi are continuously differentiable, of course, and G, capital G as well. G, the derivative of G maps X onto Y, and these derivatives are positively independent on the kernel of this method. Well, it is not actually contained, this fact, in the paper by Frankowski and Smolowski that I mentioned. It is not contained, but using some of the results of this paper, we can get it. So that was that. Sufficiently simple, I believe. I'm sorry. And there's a trivial remark that if the condition Y is satisfied for some finitely many sets, then it is satisfied only also for the union with sets as well. So, what about condition double I? So consider the set Q equal to this inequality. You remember that, it's written here, that the condition double Y is this inequality with this quantity instead of this. Right? This condition means that this set Q and this tangent cone are subtransversal in X bar. So this means that this is some analytic ways to verify that at least. But it can be shown that y, the condition double y, when we have this instead of this, is equivalent to this condition if this derivative, this direction derivative is negative for some u, no matter how this u connected with our problem. But if there is at least one u where this is negative, then this condition is equivalent. So we reduce everything to subtransversality of these two mappings. And that's already a way to offers us some way to verify the condition. I believe that I'm approaching the end already. No, I would like to say a few words just about how this applies to the problem of mathematical programming. This is the problem. We want to minimize some function f subject to fi on a negative at x, and this gx equal to 0, and x belongs to the set u. Again, all the functions and mappings here are considered, well, at least having second derivative, and continuous first derivative, and u arbitrary. This problem, in connection with the sufficient condition, without this constraint, was actually considered in the mentioned paper by Frankowski and Smolovsky. And this is the result, which we can get from the theorem. So if x bar is the local minimum of the problem, I must say that here actually positive independence of the derivative of the function is not needed here in this result. It will be needed when we pass to, well, we'll not be able already to state that. Sorry. So if this derivative maps x onto y, and if this sets G, the pre-image of 0 on the G, and u are subtransversal at x bar, then there is a gamma, positive gamma, such that this inequality holds. This is an assumption. I'm sorry, I just was thinking about sufficient condition, I'm telling you about necessary condition. Yeah, it is necessary condition, of course. So, so under this condition we have this inequality, okay, and also this inequality. This is the first order condition, and this is the second order condition. The first valid for all h belonging to Kc, and the second valid for all h belonging to Kc, and V is the second order set. Okay? And the critical count here is this set, which should be expected, of course, from the definition. This is a necessary condition. So it is. It already requires some effort, I must confess. Now about sufficient conditions in this mathematical programming problem. So let's consider this problem. Minimize such function, this function q of x, written this way. Okay, this sort of penalty function, let's say, with some gamma. It turns out that under the assumption of theorem 3, the previous ones, that G prime is onto, and so there's a local minimum in this problem as well. So we can consider this problem, as far as we're talking about necessary conditions or sufficient conditions, we can consider this problem instead of the original problem with constraints. Okay. So again, yeah, well, as I have mentioned, this P0 has the same form as basic problem, so we can apply the corresponding theorem and to get the following result. This is a sufficient condition. First of all, I have to mention that A0, well, this is more or less a trivial thing, but that the property A is now stated in this way. That for any lambda, there is epsilon, such that for any u from this difference, such that the norm of u is smaller than epsilon, and the value of our function is smaller than epsilon times u. We can find h and kc and v belonging to the tangent set, to the second order tangent set, such that this inequality holds. Okay? This is this. I will not return now already to explanation when this condition is satisfied and which condition then the element of the function is already was set. Already. And this is the theorem. If x bar satisfies the constraints of the mathematical programming problem and A0 holds, and if this long inequality is valid for all h in the critical column and all v from the second order tangent set, the next bar is the local minimum of the problem. So I wish to stop here. It's possible to rewrite this condition in terms of the Lagrange multipliers and so on, but this would require a long time. That's it. And here are some references. Well, I will not go into the details of these publications. I just want to refer to mention this paper, which I already mentioned a couple of times. And I would like to mention this book where inequalities, inequalities of that sort were carefully studied. Well, subtle society type of inequalities were carefully studied. It's a very recent book by Duni. That is it. And the paper that is also published will soon appear in the Relations of Reading Journal. So thank you very much.
Any questions, remarks, please?
In the context of second-order sufficient condition, many people consider extended critical cone. Extended critical cone. Critical cone, but with inequality which makes it bigger. So it's instead you replace consideration of extended critical cone by assumption.
Yeah, well, of course, but definitely it's better. It's preferable to have critical cone alone.
Yeah, it's nice, but these are the cost of conditions.
Of course, yes. Well, definitely, no, I understand, of course. If you extend a little bit,
yes,
you have much more flexibility to work with estimates, definitely. But, the right result should contain critical.
Another question? And what about non-Lipschitz case? Because I think this theory could
well, second-order conditions for non-Lipschitz cases.
No, first theory about it. Because your theory developed on the Lipschitz case. And if, For example, the function is not linear, just what happens?
No, there are some publications about that. So you think about first order conditions?
Yes.
There are lots of quite a few publications. I think that you can read about that. Well, definitely there is something about that. Something. I believe, I cannot say for sure. It's a big book, so I really know enough. I believe that in this paper is also no, they use no problem. In these two things you can find something about that.
Okay, thanks.
But well, they're really rather not very precise type of result. But very rude, very rough.
Another question or another? Okay, please.
Are there situations where the second order conditions are not enough? So I mean that there are degenerated problems when even second order conditions are not enough.
Too bad.
Yes, but I remember your paper very long time ago when you proved the basic theorem of algebra. You proved basic theorem of algebra by high order automatic conditions. So this was amazing result and demonstrating that second order automatic conditions are not enough, but high order are enough.
I'm sorry, I cannot, I don't remember.
Okay, let's thank again.